Section 2.5, continuity. A continuous function defined in mathematics is a graph where the line doesn't break. That is, the graph of your function, it goes nicely somewhere and doesn't do this. For example, that it might just jump over there for no apparent reason, or sometimes it might even be going along happily, and for some reason one of the values is up there, then it keeps going. When that kind of stuff happens, then it's not continuous. So the definition of a continuous function is this, that if function f is considered to be continuous at a point A, if the limit as x approach A is exactly the same as the function of f at A. When that happens, we call it continuous. Intuitively means that when you get close to that point, when you're hitting, it better be what it's supposed to be. If it's different, then the function is broken. For example, this one you get over here and it's one value, but you come from the other side, it's a different value, and you don't know which one to land. And that, of course, means it is not continuous. Now, the continuous functions have very nice, convenient principles. That is, if you have two functions, say f and g, they're continuous. That means f plus g, the function that adds together, is also a continuous function. Or minus, of course, and then or multiply together, f times g, or divided on all the spots where g is not 0, or even the composite function, f of g. That is, if you plug g right inside inside f, the result that comes out is still continuous, assuming they both are at that one point. Now, whenever a function is not even defined, then it's for sure not continuous, because then this relationship is not satisfied, because f doesn't even mean anything at A, so no way it's going to be equal to whatever this might go to, if it goes to anything at all. So one thing I should mention, that a continuous function doesn't have to be smooth. Normally in your textbook, you see a continuous function example, something like this. It's nice and smooth. But bear in mind, the continuous function can look like the stock market graph, or the lie detector test, or some such thing. It can be extremely jagged, but as long as you don't lift up your pen when you're drawing it, it's still considered continuous. Now, the next thing we want to mention is sometimes a function is only continuous on one side. For example, like the square root of function, being that the function is only defined when x is bigger than 0, so then you have to, the function is continuous as 0, but only from one side. See, the other side we don't, and there's no way you can define it the other side, so it's called continuous from one side only, which is perfectly fine. A function can be continuous on a closed interval, on an open interval, or even on the entire line, as long as this definition holds for every single point. The definition talks about one point at a time, but if it's true for every point of the domain of the function, then it is considered continuous on the entire domain, wherever that might be, whether it's a part of the real line or the entire thing. Let's look at a very, very, very simple function that is continuous. Well, we're supposed to show that it's continuous. Suppose f of x equal to something like this. You have x squared is equal to x squared sometimes, and x other times. Equals x squared when x is less than or equal to 1, and equal to x when x is bigger than, equal to 1, bigger than 1. So now is f continuous at 1? Exactly. The graph of this thing goes like this. Is x squared, okay, you draw the x squared line graph, which is the parabola, until you reach 1, and then you suddenly take a different turn and go that way, and this is exactly 1. So why is it continuous? Because the limit as x goes to 1, okay, from both sides, from the left side or the right side, is equal to is equal to 1 if it's for x squared, and it's also equal to 1 for x. Okay, it doesn't matter which way you calculate it. Therefore, f is continuous.